All right, well, thank you for coming out, everybody. I'm really excited to be here to talk. Oh, you got schedule too? We're a little bit behind, so this will get sent out. You'll see the schedule of the next classes that are coming up. Okay. So a little bit about me. My name is Scott Adams. I'm a senior data scientist at Nielsen, the TV ratings company. And this is my cat, Ivan. He thinks he's a parrot. I also have another cat named Zazzles. Not important, but if you want something prettier to look at than me, you have this cat here. It's wonderful. Make sure I'm not getting out of the way here. So I guess I'll be doing shadow puppets, so I make sure I stand in front of the screen. So just a little bit of background about me. When I was in grade school and high school, I didn't care for math, and I know a lot of this data stuff, we tend to equate it with math, and I was really not the best. I remember in high school, I could pass, but I was getting like C's in algebra. And I remember taking a statistics course. And I thought, wow, this is really cool. You know, there's math here, but we're applying it to real world problems. It's not just these theoretical formulas all day. We can actually use mathematics as a tool for prediction and making inferences and learning just neat things that can drive some kind of value. And from there on out in college, I got more and more interested in statistics as well. Started to get into sociology because I was really interested in social patterns, how people behave, but also a lot of the research methods that go with it. And ended up bouncing around in grad school for a while. Moved to Nebraska, got a PhD out there, came back here, and started working at Nielsen. I shouldn't say come back here, I'm from Cleveland originally, but ended up coming back to the Midwest anyways. So at Nielsen, if you don't know about Nielsen, one of our main products is we produce TV ratings. So whenever you see how well a show is doing, we have an estimate of how many people are watching. That's what I do a lot on the methodological enhancement side, ensuring that our data are representative of the population, implementing new techniques, new machine learning or other modeling techniques to improve how we predict things, how we measure TV audiences, that kind of stuff. It's a lot of fun, very interesting. So in a nutshell, that's what I do. And again, I have two cats, Ivan and Zazzles. Hello. Just so I walk in. So the purpose of this talk is a beginning, introduction to data, and also, I guess the subtitle for that could be demystifying data. So data is this big buzzword now, and if you came from another planet, you might think like, wow, these people just invented data, and so we're always talking about data-driven, data science, big data, data. It's really nothing new though, right? It's been around with humans forever. If we go back to about 18,000 BCE, we saw first evidence of data recording in what are called tally sticks. So these were found in Uganda at that date. And individuals would take pieces of bone or pieces of wood, and basically they'd put little notches in it to make records of transactions, make records of weather, what have you. It was a numerical counting system. And this is some of the earliest evidence that we have of humans using data recording and data analytic techniques. Jump ahead, about 2400 BC, the invention of the Abacus, a tool that still eludes me, but it was essentially the world's first calculator that you could use to get calculations really fast. I watched a YouTube video on it to try to refresh myself before this class. I just don't get it. I will never get the Abacus. That's okay, though. Jump ahead to 300, and this isn't linear. This is just some milestones that were kind of interesting to me. Look at other ones if you want, but we had the establishment of the Library of Alexandria, which in this time was the largest collection of information that humans had known. Of course, it got destroyed, but actually a lot of information was preserved. Okay. Let's jump ahead to 1663, a lot further ahead. John Brown, he was a statistician in England, and he developed what many consider to be the first statistical analysis, and also development of what we would now consider epidemiology and demography. So what he was looking at was he was interested in predicting health trends, and in particular looking at predicting the bubonic plague, if that would come about. And at this time, data, we didn't have a lot of accurate data recording mechanisms. A lot of times it would be a village parish priest who would take rolls of births and deaths and marriages, other things that we refer to now as vital statistics. And what John was doing was he was looking at the birth and death rates at a given time. And basically, in a given time, you'd say, well, if the probability of a 20-year-old right now of dying is the same as the probability of a 50-year-old, that would suggest that there's not a big age factor going on. There's something else that's driving mortality rates, which might be plague or other kinds of diseases. And that was really useful in predicting diseases and really saying, hey, people in London, maybe if you can, you should move out to the city for a while. It looks like the plague is coming. Not good. And you can conjure images of Monty Python, the Holy Grail, bring out your dead, ring, ring, whatever. You've seen that. So let's move ahead to within last century or so, 1940. How many of you have seen The Imitation Game? It's a movie, cool, a lot of you. So Alan Turing, he's considered by many to be the father of modern computing, and he created this, well, actually, he improved on this device called the bomb. The Polish actually developed it first, but he improved on it to encrypt German messages to decode what was called the German Enigma machine. And it was this first example of using this electronic encryption machine that could decrypt messages, essentially decode these messages. And it's credited for reducing the length of World War II by, some say, 2 to 3 years. So it was really, really important innovation, and also was the precursor for a lot of modern computing that we think of now. We owe a lot of debt to that event. Jump ahead to 2005, said big data, another one of those catchphrases. But in 2005, there's this article published by O'Reilly Media called What is Web 2.0? And that's when the term big data really was first used in the modern context to refer to huge, huge quantities of data that can't fit on a single computer and that are just simply not comprehensible to the human mind and to a lot of modern mathematical methods that we have. Okay. And I forget which arrow does what, so bear with me for a moment. There we go. So from this timeline, what we see is that within the last 100 years or so, there's been a really, really huge exponential growth in technology, computing, and a lot of other machinery that allows us to do the high-scale data analysis and data science that we see everywhere around us right now. And what really drove that? Well, a lot of it has just been growth in the efficiency of computers, the computing power, and also the cost of computers. So has anybody seen one of these machines ever? This was the first hard drive ever. So it was introduced in 1956, the IBM 305 RAM AC. And so I wish there was a way to turn off the lights over here, but hopefully you can see it enough. This is the actual hard drive over here. And then you can see for scale, the hard drive's back here. This is a person working out front. This thing was huge. It weighed 1 ton. It was about the size of 2 refrigerators. And IBM, their model was they didn't sell mainframes like this. They would rent them out. So that would cost this machine that had 5 megabytes of RAM, 5 megabytes of storage, I should say, actually, cost at the time $3,200 per month, which would be about $30,000 today. Just to give you some context, this 5 megabyte of storage, that's less than 1% of the hard drive size that I have on this little 2015 MacBook Air. So we have come a long way. So what is the result of this? We've had these exponential leaps in computing power, in data storage capabilities, especially within the last 2 decades. And this article was published in 2013, but this was the estimate that of all the world's data, and again, data is nothing more than information. It's been with us all along. But 90%, we estimate that about 90% of the world's data has been generated in 2013 within the last few years. Okay, that's really astounding. And a lot of this, of course, this growth in data generation has been driven by the development of the internet. all right? So the internet allows us not only in terms of server developments that are everywhere that comes with it, but also in terms of the various technologies for collecting data. You can think of your smartphone, think of visiting websites. There are just so many possibilities for data collection. Surveys are great. I'm a survey researcher by training, but there's also a lot of other electronic methods for data collection that we have now. And this has resulted in just an overabundance of data. And that's a big reason why today you hear all these buzzwords, because one, there is a ton of data out there, and two, more and more companies are realizing that there's value in data and there's value in working with data in various ways. So what are some of the ways that you might have encountered in your day-to-day life, or still see that companies work with data and drive value? Can anybody guess what I'm trying to show here? Spam filter, yeah. So I don't have kids, but I like dad jokes a lot, and this is like my visual dad joke here. I don't like spam either, but I like coffee, so it works. Bear with it. Am I still on the screen? Good? Yeah, okay. So if I'm out of the screen, just somebody tell me and I'll come back. But I want to make sure that everybody can see the spam, the glorious spam up here. So spam filters, the way they're designed is that a company like Google or any other email provider takes a bunch of data on different messages, on different words that come up, and basically predicts the probability that a message with certain words in it is something irrelevant to you, or something that is relevant to you. One of my favorite examples, I have these different data science books that I enjoy doing exercises out of, and one of them talks about a spam filter and looking at the probability that a message is spam given that it contains the word Rolex in it and Viagra. So maybe the Viagra part is spam, but I'm kind of drawing the blank where you'd see a message with Rolex and spam, but it could just be a big list of things for sale at Costco. Who knows? Aaron and I love Costco, so I've got to give a shout out to that. He's over there almost choking on whatever he's drinking. Another one, Dominoes. Dominoes has been this surprising success story in e-commerce. So for a while, Dominoes was like this kind of dated pizza company from the 80s, and they've really come back with a vengeance. And part of what has made them relevant again is that they have this platform called Dominoes Anywhere. And you can order a Domino's pizza on devices like Google Home, Alexa, Slack, Messenger. There's commercials about ordering it on the smartwatch. A bunch of different devices besides just traditional calling in that you can get Domino's pizza. And one of the advantages of that is not only do you get a pizza, Domino's gets a sale, but also that Domino's gets a lot of data. And so they can predict even within a household, within a household you might have different devices and some of these different platforms. They can predict within a household who is likely to be ordering what, and they can tailor their promotions and their ads to specific individuals. This data allows them to develop predictive models for that and better target potential customers. So it's a really cool thing. They got fun commercials too. Have you seen those commercials where Domino's going out and paving potholes or whatever? That's kind of cool. Have you seen these machines, the Coke Freestyle machines? Yeah, they're pretty much everywhere now. Do you know that they collect data? Has anybody tried Cherry Sprite? Seen it come out? So Cherry Sprite is a newer product that Coca-Cola released, and really it came about from this machine. So the people at Coca-Cola, they were looking at, what kind of combinations are people making? You don't have to just have Fanta or Coke. You can push different things. I remember when I was a kid, I was always so excited to go to Burger King because they had this fountain machine, and I'd make a mix of like Dr. Pepper, Pepsi, iced tea, Mountain Dew. It was disgusting, but I thought it was the coolest thing in the world. And it's a similar thing to this, but hopefully that's not coming up in the data. But Coca-Cola is looking at, what kind of flavor combinations are really popular. One of them they saw was this cherry and Sprite combination, and they released it. So you can see how something like this, having data on what your consumers are doing, can drive new products that are likely to be a hit. Now, don't worry, this is the only mathematical related slide in here, so don't worry about this. Traditionally, when we've looked at data analysis and statistical analysis, we're trying to predict something, right? So in this really simplistic example, I have data on cars. I'm trying to predict miles per gallon by weight. As you can imagine, as the weight of a car increases, miles per gallon tends to decrease. So we have an inverse relationship here. And typically how we would do this is we have a closed form equation called the ordinary least squares equation that finds a line of best fit that best fits the data point and basically is trying to minimize the distance between this line and each data point. Does anybody remember this from algebra? Do you remember y equals mx plus b? Some of you are crying. It's okay. Well, one of the issues is that when I was talking about big data, data that doesn't fit on a single machine, that's not really comprehensible to the human eye, solving these equations becomes really computationally difficult, computationally expensive, and takes a lot of computing power. So what data scientists and machine learning practitioners have come up with is new ways to analyze these large quantities of data. And so I'm sure we've all heard of the term machine learning, right? So machine learning, you can think of this as an alternative approach to this closed form equation that I showed on the previous slide, which, by the way, statistics, if you have data that this can work on, the equations are still great, they still work, but in some cases, that's just not realistic for some of these large quantities of data. So what can we do to get around that? Well, machine learning practitioners and data scientists, basically this is a simplistic example, but the idea is that you randomly fit lines through these data until you find a line that best fits these data points. So we might start with something, it's kind of hard to see, but a line here, that doesn't fit the data really well. Okay, let's try again. Okay, this is looking a little bit better up here. Okay, we're getting a little bit warmer. And basically, you go through this iterative approach, this algorithm, to fit these different lines until you find one that best fits the data. And we have our green line again. So when you hear machine learning, it's another one of those buzzwords, and we like to talk about it, but exactly what is it? And in a nutshell, that's what it is using this algorithmic approach as opposed to some kind of equation to find out predictions that best fit the data at hand. And then you can use that predictive model, this line, you can assume that it's going to repeat itself going forward, a big and dangerous assumption, but assumption nevertheless. And so if you have new data points that you haven't seen, you get their value on the car weight, for example, we can get a good prediction of what their miles per gallon is. And that's where the value is in these machine learning models, is that you can make predictions on what someone or any data point is going to do in the future. So the basic idea here, what I want to stress is that the quantities of data, the growth in data, and the computing technologies that have gone with it have necessitated new approaches to working with the data. Okay, how many of you have seen this Venn diagram? A few of you. So this is the traditional definition of a data scientist. You want somebody with math and statistics knowledge, hacking skills, and some kind of substantive business expertise. And a lot of the companies that have really driven the growth in the data science methods, you can think of like the Googles, Facebooks, Amazons, they've been looking for people to grow their businesses that have these skills, and this is a relatively new skill set. It's also very difficult to find somebody that has all these skills, leading to the idea of the mythical data science unicorn. And the unicorn, another nice image, I hope you like this as much as the cat. The unicorn was necessary when a lot of these large data companies were getting started because we did need new ways to approach problems that weren't just traditional research, that weren't just hacking skills, that were a little bit more than machine learning, but also was something that we could build business value out of. And that certainly played a role. But as data science has matured, what we're seeing more and more is a focus on differentiation. focus on not just finding a unicorn, because one, they're hard to find, they're very expensive, but building teams of data scientists with different skills that are also complementary to each other. So you might have on a team a machine learning expert, but okay, maybe you need a little bit more than that. Maybe you need somebody with a little bit more business savvy, so you need a data communicator, somebody who can go with people who are making decisions or clients, but also understands the data. Maybe you need somebody to visualize the data, so you need an expert in data visualization methods, an expert in Tableau, for example. Maybe you need somebody to run statistics or do exploratory data analysis. Shameless plug here, these are all things you can learn at a Promotable class. And with that, with this focus on differentiation, there's this idea of the business intelligence gap too that's out there, is that what we're seeing is that the quantity of data, as I mentioned, it's growing at an exponential rate. But as the world becomes more interconnected, competition becomes more fierce, and the time to decide is decreasing as well. Also, we're just communicating with each other faster. So what there is a need for is what they're calling these business intelligence skills. But what this really refers to is people with a good sense of business strategy, a good sense of business acumen, but who are also very, very data literate. So maybe it's an individual who is not an expert software engineer, maybe not an expert mathematician or statistician, but they know what a machine learning model or statistical model is. They can see results and say, oh, hey, that looks okay, or that's interesting, or tell some kind of story, or at least question the results. And that's really important. This skill set, this is the prediction that this skill set will become increasingly important. So that's the point here, is that you don't have to necessarily be this super hacker, coder person, whatever, to get into data science, to get into the data conversation. Nothing can substitute an inquisitive mind and somebody who questions results, and somebody who also, walking this line between understanding data and understanding the methods for analyzing data and how to use these to drive value. That's a pretty cool thing, and it's a pretty awesome talent, and it's very necessary. Why is that necessary? Sometimes we suffer from big data hubris. Big data are awesome. Having large quantities of data, it's awesome. But if we don't question our assumptions, if we don't question the assumptions behind the models, we can run into problems really, really quick. So this is a graph showing what's called Google flu trends. Google developed this approach. They could look at their search data, and based on queries that people were putting in, they had a pretty good estimate for a while of when flu would break out. And this whole idea, this kind of goes back to, it's consistent with that, with what John Gaunt was doing with the statistical analysis in London for predicting plague. We can better prepare if we know that the flu is coming. And let's see, where is it? The orange line up here are the estimates of how much. I think it's the percentage of the population that's going to have the flu. Basically, bigger peaks are worse here. The flu is coming. That's all you need to know about this. And then the blue line here is the CDC data. So CDC monitors national flu prevalence, incidence rates. And for a while, you see that Google Flu Trends is mirroring this. And one of the nice things about this is that the Google Flu Trends data, it's out there. It has lots of data points and a little bit more cost effective than some of the CDC data to make these predictions. But then we had this big divergence. Google was predicting nearly double the rate of new flu cases at one point than compared to the CDC. And what happened here was that Google's constantly tweaking their search algorithms, so we have different data going in. And also with all the data that goes into this kind of model, just by random chance, you're going to have things that are correlated with flu, but aren't really predicting flu. So for example, you have people searching for the high school basketball season. That could be some kind of predictor of flu in the past. But what was going on was that a lot of these other terms that weren't causal predictors, let's say, of the flu were coming up in the past, and Google used these terms that weren't necessarily relevant to build this model and said, whoa, look at all these people searching for high school basketball. A big flu outbreak is coming. Not the case. And so my point in telling this story is not to disparage big data. Again, it's awesome. But if you're not questioning the algorithms you're using, if you're not questioning what's going into your model, you can end up with in a lot of trouble. A big difference between machine learning statistics that you'll hear is that statisticians or business intelligence individuals are really focused on predicting past events. And that's part of that big data hubris that, well, we don't predict the past, we can predict the future. But a lot of these models on big data, actually all of them, are based on the assumption that the past data that you have to make these predictions is going to repeat itself in some way. And if there's some kind of major changes in the population that you're looking at, the sources that you're drawing data from, you're going to end up with something like this. You're going to end up with bad results. Data is great, but really the issue here is having high quality and relevant data. Okay? That's really what is key here. And this is nothing new. So in 1936, there was a presidential election between Alf Landon and Franklin Delano Roosevelt. And Literary Digest had this pretty awesome poll. It was huge. It had about 2.5 million responses. And it was based on a really large data frame of telephone numbers and auto registration records. At the time, phones and automobiles tend to be more highly concentrated among richer individuals. So what happened was this Literary Digest poll, it was huge at the time. I mean, there was 2.5 million data points. The Gallup poll at the time was about 500,000. It was a lot bigger, but it was based on biased data that wasn't relevant and wasn't accounting for those in lower socioeconomic strata. And thus, it missed and had to publish this, our face is red. So these data mistakes and just assuming that, okay, we have more, it's better, this has been around forever and we don't want to repeat this trap. So that gets to my point of really having a critical eye and being able to question what's going into a model. It's really one of the most valuable traits I think you can develop. And again, not disparaging big data, but there's other things out there too. Some individuals have been saying, well, we have all this data out there, but not every company is Google or Facebook or Amazon. What about other companies that might not have that quantity of data? Is there any value on it, or should we just throw it away? And the answer is no. There is value. And if you're a smaller business, you might have receipts of what customers are buying. You might have some kind of advertising campaign on your website. You might be able to track web clicks. All these things are really valuable sources of data. What is key is just knowing how to work with it, knowing how to ask the right questions. So there's been more talk that I've been seeing is this emphasis on small data. Now the concern here is that we could go too far in the other direction. Now, small data is the big data, that's so 2000, I don't know, when did I say it? 2005 it was coined, 2013, whatever. Small data is the wave of the future. That's something that we don't want to do, okay? That's going too far in the other direction. The point, again, it's not the size of the data, it's are you using useful data? If it's small data, great. If it's big data, that's cool too. But look for useful data. So now I want to talk a little bit about the tools that data scientists can use to work with data. And I am going to take a drink of water there because I sound like I'm going through puberty if my voice is cracking here. Can you nix that from the record when I say stupid things like that? So a number of common tools that you'll see in the data scientist, data analyst toolkit are things like scripting languages, R and Python, for example. These allow you to write code and perform a variety of statistical analysis, data manipulations. The big difference between Python and R is R was developed by statisticians. So if you're doing more traditional statistical research, if you're focused on standard errors, on population inference, there's a lot of really, really great libraries in R that are for that. Python just doesn't have. Python developed as a general purpose language. A lot of web development occurred in Python. And recently, a lot more data analytic libraries have come into Python too. And when I talk about libraries, it's just basically a set of code that provides tools so you don't have to code functions yourself every time you want to run something. So Python has been more of a general purpose language and has been adapted more and more for high-level machine learning algorithms, predictive modeling. But a lot of the basic data analysis tasks that you want, you can accomplish them in either. There's sometimes this Python versus R battle, but really it's choose the right tool for the job. Excel, you can do a lot in Excel. Exploratory data analysis. So you have your data, you want to look at maybe the distribution, the mean and standard deviation. You want to look for missing data. You want to get some kind of idea of what questions to ask or what might be going on. Excel is still a great tool for some of these things. And one of the things I want to emphasize is that if you don't have any background in programming, if you find it to be a little daunting, open up Excel and use some of the functions, like highlight a column and use sum, A1 through A13. What you'll see is that a lot of these functions there in Excel, the syntax is the same in other things like SQL or R and Python, or it's very similar. I mean, really, those functions in Excel, if you're worried about coding, that's really the first step to get an idea of what coding is like. Another thing that I see is when people are making the jump from a program like Excel or Google Sheets is that it kind of freaks them out that in these programs, these spreadsheet programs, you can see your data, but you move to something like Python or R and you just have this blank text file. It's like, where'd my data go? Your data are still there. It's just, you're actually explicitly programming instructions. So that's okay. We've all been there when we've started programming this kind of, oh my God, where did my data go? But it's something with practice that you get used to. SQL stands for Structured Query Language. So I mentioned that we have large quantities of data, and they often reside on what are called databases, which are just large collections of data tables, kind of similar to an Excel data frame, something like that. And SQL is the standard language for pulling data, maybe doing some very simple analyses like means, standard deviations, like I said, on the data. SQL is not great for more advanced analytics. That's where you do something more in R or Python. But in terms of actually pulling the data that you need from a large database, a large media data lake, something like that, SQL is the go-to tool. That's hard to say. And it's really, if you want to get started off, if you know Excel, if you want to learn any of these aside from Tableau and want to learn a programming language, I think SQL is a really good place to start. It will probably give you the most bang for your buck. Tableau is a really, really nice dashboard piece of software. It creates these really great visualizations. I just want to give you an example. I want to exit out of this for a moment. I know I'm going off screen here, but if you've never seen Tableau, so there's a site called Tableau Public. It's the Tableau site, and they have a gallery different things these different dashboards that people are doing. So this is a really cool one. Captain Marvel is a movie that just came out. And I don't know what this map is, but they're predicting all sorts of things that are related to Captain Marvel, related to pilots or something. I didn't really look at the context, but these are the kind of cool things that you can create with Tableau. Let me see if I can find something that's a little bit more. Again, substantively, I don't know what the message is here. I don't have context for it, but you can create these. One of the cool things about it is if you're into geography, you can do geospatial analysis, create these really nice looking maps really easily in Tableau. And the idea of a dashboard is, I kind of think it as this souped up. You remember like science fairs, with the science fair presentations, you had that 3-part poster board, whatever, and you put, hey, here's my hypothesis, my data, my results. A dashboard's kind of like that, but even better and prettier. And the Tableau, it's really user-friendly. When I was teaching at Promotable, it's the one piece that people like the most, and my students were doing really, really creative things with it. I think one of the most creative was one student was looking at the count of swear words in Quentin Tarantino movies. That's what he wanted to do. I thought it was pretty funny. So I can go nuts with it. And with that said, these are some of the different toolkits, and a lot of times, oh yeah, hi.
I have a question.
Yeah.
Could you shed some light on Power BI versus Tableau?
Yeah, so Power BI is another tool. It's very similar to Tableau in terms of dashboard creation, these visualizations. The difference is Microsoft product. In a nutshell, it's a Microsoft. I mean, there's going to be some differences in the syntax or the drag and drop tools, but it accomplishes pretty much the same thing. And I think if you know Power BI, you could go to Tableau pretty easily, and vice versa.
But in terms of which one is better in terms of features, is there a very big difference? Because previously there was a
Yeah.
perception that Power BI was not as strong.
So I'm not as familiar with Power BI. I've looked at it a little bit, and I am aware of that perception too. I think recently Microsoft has looked at the success of Tableau and has beefed it up a little bit. A lot more job. What I'll say is just my own opinion is a lot more job calls you'll see Tableau advertised as opposed to Power BI. That might change in the future, but in terms of if you're going to invest in one, I would probably invest in Tableau, but I think it's pretty easy to go between the two. I mean, the key here is having both a data analytic mindset and also maybe some visual design background to create these cool things. And it's just as an aside, I talked about differentiation in data science, and one of the roles that I see popping up is like data designer, I think it's called. We look at people to create dashboards like this and to take data and visualize it into results that are easily communicated to other stakeholders that might not be particularly tech or data savvy. So if you have an interest in data, you like making pretty things, go for it. Like my wife works for Allstate, and her main job is she makes a lot of dashboards, a lot cooler ones, a lot nicer ones than I make, so I'm not going to show you anything I made, but you can do some really cool stuff with it. So in terms of how these workflows are used, a lot of times what you'll see is not just one workflow, but you'll see a combination of different tools. It's not one or the other, but it's what tools and in which way work best together. And in some cases, you'll see things like querying data, looking at a large pool of data to get the data that you want, running a SQL query, maybe exporting that to some format, like a CSV file, then analyzing it in Python, run some kind of predictive model, other kind of results, and then presenting your final results, not necessarily the gory details of the model that you have, but the final predictions or whatever in a Tableau dashboard. And this is actually the data analytics course that I taught at Promotable recently. This is kind of the framework that we applied, is that we started off with actually some exploratory data analysis in Excel. Students would download data from CAG or a different repository, take a look at it, learn how to do some stuff in SQL, some basic queries, some analysis in Python, and then so they had a lot of fun presenting this in Tableau and going nuts. And I mean, it really is a fun program to play with. You can waste a lot of time with it too. That's the danger with it, but it's really fun to make some of these dashboards and present nice visual results. There was one student who was using a Titanic data set, and he was looking at basically just different predictors of survivorship. And he put the picture of Leonardo DiCaprio and Celine Dion on his dashboard. It was really nice. So when he was presenting, I played the Celine Dion song, and we all had a laugh. We cried a little bit too. It was pretty nice. For a lot of things, I said a lot of stuff you can do in Python, you can do in R, and vice versa. So you could swipe out R and have a workflow that looks like this too. In some cases, you have an Excel data set or just a CSV file, and you can read that right into Tableau. One of the cool things about Tableau is you can really read like any data into it. You can read geospatial data from the government, for example, from the census. You can read Excel files, comma-separated value files. You can connect it to SQL. You can connect it to a database and run SQL queries right from there. So there's a lot of stuff that you can connect to Tableau. It's not just the standalone thing. You can incorporate a whole ecosystem around it. And in some cases, as I alluded to before, this might be your workflow. You get some kind of file in Excel, and somebody's asking for some basic descriptive statistics. For example, what did sales look like in the past quarter, past month? That stuff, this is an example of small data, but that stuff can be easily accomplished in Excel as well. So again, it's It's choose the right tool for analysis, what's going to be most effective, what's going to get the job done, what's going to do it right. One of the nice things I will say about scripting languages like Python or R is that when you code, you do have a record of your analysis that's not there in drag and drop tools like this, but if you're doing pretty simple stuff, you know what you're doing. But this is why a lot of data scientists, statisticians, programmers prefer these scripting tools, is that you write something and you go back, oh, there's a mistake in it. You can easily see what you did and make adjustments to it rather than going through a drag and drop method. So that's one of the advantages of learning a programming language I'll throw out there. All right, so that's the end of my talk. There's some contact information up here. And I wanted to be sure that we had a little bit of time for any questions that you might have. Yeah?
What's an example of a SQL tool that will run on your MacBook Air?
So an example of a SQL tool is a program called DB Visualizer. So you can get a free version of it. And it's a little bit complicated because you have to have an actual database to connect to. So it's kind of like connecting to some remote server that hosts all the data, but you can use DB Visualizer to write queries and actually pull data and see what's going on natively on your machine. That's a good question. So the difference between the free and paid version is that the paid version, you can have a lot more tabs open, but the free version you can't. There's also other online tools. W3 School, for example, is a really great website for practicing SQL. They have these databases and tables there that you can write SQL queries and just write on your web browser, practice with it. Mode Analytics is another company that allows you to do SQL, R, and Python all in one framework. So if you want to practice, there's certainly tools out there for you. Good question. Yeah?
You mentioned trend towards small data analysis kind of evolving now and then becoming more prevalent. What are the differences in the approaches between a big data analytics initiative and a small data analytics initiative?
Yeah. So a lot of it is in time and computational power. For example, at Nielsen, a lot of the custom analysis that I get in, if I'm doing some kind of statistical model, descriptive analysis, I can do that within a few hours, and most of that is spent thinking about what I want to do. It runs right away. Some of the more complex models that we have with, for example, return path data, so data coming in from Comcast or DirecTV, could take 1 to several days to actually run a model on all that and get our predictions. So that's one of the big differences, is that with big data analysis, this is why a lot of computer scientists are in data science, because you have to think about computational efficiency, computational power, because these things, if you're running something for a while, you're running on Amazon Web Services or Microsoft Azure, they charge you by the amount of time, amount of computer power that you have, so you want to be sure that it's really efficient. And another big difference, too, is this gets to the difference in the paradigms between statistical research and predictive analysis or machine learning. A lot of these big data methods, they're really good for pulling this data, getting accurate predictions. So you can think of like Netflix, for example. You have this, we're going to recommend that you watch this based on this show. And that's based on just large quantities of data of what not only you're doing and watching, but what other people are watching. This data, based on people with similar patterns in their data as you, this is what we think you'll watch. It takes a really long time. But if you were to go into that model and really see what's going on in there, it'd be hard. So there's often this term that a lot of big data models are like black boxes. The focus is really on prediction. It doesn't matter. You want to just whatever variables you throw in, as long as it gives you the best prediction, that's what's ultimately key. For a lot of small data analysis, statistical analysis, the framework is more on inference. So we want to actually look at what the model is doing, and we want to interpret some of the individual parameters that are in our model and make some kind of substantive decision or contribute to some kind of theory about what's going on. So you wouldn't see a statistician just being like, let's throw in whatever, I don't care what these variables are doing in terms of prediction, as long as we get the best outcome, as long as we get the best predictive model, as long as we can take this model, throw it out into the wild, and if we get new data points, it's going to predict somebody's output. The statistician will be more like, whoa, we got to think about what these variables mean. Are they really measuring something that's out there in the real world? It gets more at causality. That's what the focus is on. Hi.
I have a question for you. So you said a lot of, we call it big companies, and they have a big data. What about the other companies? Can you talk about the strategy that a company can like do this digital transformation in data science? Like, where do you start then as you as a data scientist? Like, what's your first question you're gonna ask, and then how do you drive the strategy for the company? Because I know that the strategy can be driven by the IT, but also you as a data scientist have to tell them how to get there.
Yeah, you absolutely do. And for those of you who maybe didn't hear the question is, so for companies that aren't Google or Facebook or Netflix and don't have that kind of data, how do you develop a strategy to work with the data? And a lot of it's going to be driven by IT, but you have to give them a roadmap too. And I love the question because what it gets at is really this importance of data literacy. Even if you're not in IT, even if you're not an expert programmer, you have to have some kind of roadmap and some kind of idea of how to work with data to direct an IT department or a machine learning department to work with that data. Now, in terms of what can you do with data, this is where the importance of small data comes in. So most companies don't have the amount of data points that Google or Facebook does, but they do have a lot of consumer data. They understand their data well, and you can still use that data on perhaps a smaller scale to make predictions. So for example, Walmart is a big company. So it's maybe not the best example, but in terms of what they're doing, they've had a data-driven pivot to compete with Amazon more and more. And one of the things that Walmart does is they look in their stores and they look at what products are selling well, what products are not selling well, and they use that data to make decisions on, well, what third-party products should we stock and when. And I think that's something that's applicable to any company. You can look at your sales data. You can look at, certain seasons. Is something selling better than this other product? Should we continue something? The idea here is that you have empirical evidence to inform your decision. You're not just going from your gut saying, well, I don't like Fruit Loops. I don't like Toucan Sam, so let's get rid of that. You're saying, well, it's not selling well. Maybe we shouldn't order this many Fruit Loops. I don't know why I came up with Fruit Loops example, so don't ask, but there it is. So I think, a lot of the questions is just, can we make predictions that will optimize our supply chain, that will optimize what we have to buy, that will optimize things that are attractive to consumers? I think those questions are universal. Whether you have small data, big data, I think you can really get predictions out of that anywhere. And also survey data, don't discount surveys. So a lot of stuff, the other thing I want to mention is that a lot of the existing data that we might have from online or different sources can address a lot, but there's certain things that we can't get at. So people's emotional states or their preferences or something. That's where surveys can be a good supplement to a lot of these data methods. So with that, the other thing is don't just think about one data source that you're going to just stick to this one thing. Think about different complementary data sources and different complementary methods that can give you a fuller picture on the problem that you want to tackle.
That is actually one of the things that keeps coming up in my head is when people ask me for example, if you're working on something that is humanitarian, they don't have access to Google, so you can't really look at Google searches. They're texting, so it could be a crowdsourcing that's the type of data that you're working with. So it is project specific.
Yep.
So it's neither one nor the other. It's something completely different altogether.
Yeah, exactly. It's not, we shouldn't be asking, is it big data? Is it small data? Is it useful data? Is it measuring what we want to measure? Is it going to help us accomplish our goals? I mean, that's the problem with these buzzwords like big data. We all want to work with big data, but maybe you don't need to. If somebody's asking me what was the average sale like in the last month, I'm not going to be like, well, I got to go to Google and download all these data and then run some kind of complex model. Well, that's something I can accomplish in Excel, and then I'm probably going to use the right tool.
Did you
Yeah, so for example, if a client is unhappy with their ratings, we'll go back and look at historical trends, what's been going on, make sure there's no mistakes on our end. Also internal stakeholders, if we want to test new products and maybe look at test and control case, so we test this new product, look at how it performs on various key performance indicators versus our traditional product. I'll take a look at that. I'll make dashboards, for example, in Tableau and present them at meetings and address any concerns that our stakeholders might have.
Can you maybe share an example where you've done that and maybe, you maybe were challenged to convince, assuming part of that role might be convincing your stakeholders to make a certain decision based on the data they presented. And did it help you maybe learn maybe a different way of presenting the data next time?
Yeah, so there was a recent case with a client. They were concerned about their ratings, and they were asking, like, how can these numbers be? I'm not going to go into too much detail for confidentiality, but essentially I looked back at the historical data, looked at what their ratings were, looked at any data I could pull addressing their concerns, and put together this really nice deck with a lot of nice predictions on it and graphs, and presented it, and the client just wasn't buying it. I mean, I had the evidence there. We looked at it, we did everything we could, and the client wasn't buying it. I don't know if there's anything different I would do in that case, but I think the lesson is that, sometimes you can do things the right way, you can have the most evidence, and somebody's not going to buy it. There's still a lot of people out there who want to go from their gut, who don't want to really understand the evidence, who don't want to buy it, and that's okay, that's understandable, that happens. But my main concern is that I do my due diligence. I provide an evidence-based approach. I'm not just going off my opinion of what's going on, but I'm actually backing up what I'm saying with facts, or at least empirical evidence. Facts is a controversial term now, or whatever. Hey.
I didn't understand, so when you were going through the data flows, the one that said SQL, Python, to Tableau.
Yeah, so that's one method that we have.
So I guess I was understanding Python in general, computer language.
Yeah.
That's why I was confused how it kind of fit in with data flow.
Yeah, so a lot of times you have data, and I say a lot of times, but most of the time if you're working with really large sources of data, it's not stored on a local machine, it's stored on some big database or what's called a data lake. So it's just a collection of various pieces of information. And SQL is kind of the default tool for what they call querying, for looking at these different tables. Again, a table is just kind of like, you can think of it as a single Excel spreadsheet, but it just has some of the data you need, but not all of it. So the idea is you combine all these different pieces of data that you actually need for your analysis together in SQL, then get that data in some kind of format that you can actually send it to Python, do more advanced analyses. So Python just doesn't have the same kind of capabilities by default for going into these databases and actually combining the data sources that you need together and pulling them into some kind of format that you can use. So that's what you'll see, is that you start with querying the data just to get the relevant data, the relevant variables that you need, and then you put that into Python or R, some other kind of language, or even just write to Tableau and start doing more advanced analyses on it. Because if you want to run some kind of really complex machine learning model or even some more complex statistical models, those capabilities just aren't there for SQL, so you have to use a different tool.
So for a huge, large data set, you want to start with SQL, you never want to start with?
I mean, there are, I don't want to say never. I'd say most of the time you probably would start with SQL, because there's so many tools out there in Python that are just beyond me, yeah. But in my experience and knowing people from different organizations, SQL is often the start for actually getting your data. Hey.
When you're stripping something in R, Python, do you use pseudocode, or how do you,
When I'm, did you say stripping it?
yeah, how do you begin like a major project? Do you use pseudocode and flowcharts to kind of draft out what you want to accomplish or strategy?
Yeah, that's an awesome question, and Here's the unfortunate academic in me saying, well, it depends. And it does depend on the project. I don't use pseudocode a whole lot. And pseudocode it's not a specific language. It's just like kind of the steps that you're going to take in terms of cleaning and writing your analyses. Some people, it works for them. It's just not something I've ever done. But what I start with, and what we often teach at Promotable, is exploratory data analysis. So get your data, look at what the distributions look like, look at missing data. And before all that, I should say that you have some kind of question or some kind of problem that you want to address. You don't just go into data looking at it. There's some kind of purpose to drive you into actually looking at the data in the first place. So yeah, I'll look at a lot of how are variables coded, how much missing data are there, should I collapse certain categories on a variable, how should I work with it? So a lot of those things before I really dig into any complex modeling. If I want to choose what variables I want to put in a predictive model, I'll look at like correlations among the variables, what would likely make a good predictor. And then from there I go on to actually developing some kind of model or analysis and outputting the results in some kind of visual format that I can explain easier to students. So yeah, I think that exploratory data analysis component is really, really key. And I think if you don't do that, you'll run into problems later. You won't understand why something broke. So I can't emphasize that enough, the importance of the exploratory data analysis. Yeah. Yeah, starting's the hardest part, right? Yeah, and despite what I said, so that's more of an ideal. It's more a do what I do. I mean, do what I say, not what I do. I do the same thing. I get excited. I start scripting right away. But projects that I found useful are, I kind of take a minute to collect my thoughts. Maybe just writing them in a notebook, the steps I want to take. Something that gives me some kind of guideline or an outline of where I want to go with this. A lot of times, projects we work on Nielsen too, we actually write up our specifications of what we want to accomplish and the steps we want to take. Now, a lot of those, with any project, they break down at some point, but it still gives you a guidepost of where you should be and where you're going. So the key here that I think you're hitting on is it takes discipline to do that. And it's an underappreciated skill or trade or practice to do that, to really sit down and plan something ahead of time, but it's a really good practice if you have that discipline. Sure.
All right, folks, thanks for...
Yeah, thank you, everybody.
Yeah, thanks for... Thanks for the amazing talk. So Scott and I are both going to be hanging out a little while longer. If you want to come and ask personal questions. I just figure we don't want to have everyone's time tied up by highly specific things, but we're going to be here for a little while longer. Feel free to come and say hello. If you're curious about the class, come ask me, or just want to get on the list and make sure you come to the next event, or just come say hello. Either way, I'll be here for another 10, 20 minutes or so. Feel free to come say hello, and then hope to see you next time.
I got more cat pictures.